And so, what's up guys? Do you know that before coming to the stage for a live performance, Vietnamese artists commonly burn incense sticks to worship the first and most influential legend in the profession? If we, shader designers, do the similar things, who would be our god? My answer is Pixar. Why is that? Welcome to the second video in the Unity Shader Graph series, and you are watching Avalanche. If a person creates a new entire industry for himself, or at least his influence is so heavy that many people follow him, then I think that person would be considered as some kind of god. For me, the god of shader is not a person, but an animation company with the name Pixar. Yes, that's the Pixar, the famous Pixar I'm talking about. In fact, the term shaders comes from Pixar's RenderMan software launched in May 1988. The usage of shaders impacted the whole world. It became more and more popular that computers started to support shaders. Then we could use shaders outside RenderMan. But it's a story from 40 years ago. Shader has acquired dramatic development since then and became a crucial part in computer graphics, but it's still so mystical for so many people nowadays. Why? I put together 4 major issues. The first barrier in approaching shaders is that you have to know how to code. That's why shader is so infamous for not being friendly for artists. Secondly, the shader code is quite hardcore, even for programmers, because you have to know about trigonometry, mathematics, and physics to understand shader code. Thirdly, the shader code has an unfamiliar structure to most of us, especially when it is designed to execute in a different fashion on the GPU, not the traditional CPU. Finally, the workflow is so inconvenient. Errors are only found after compiling, and the error message is not quite helpful. And it explains why it's so tedious to figure out what's wrong when shader doesn't work. There must be more intuitive ways to deal with these problems. And yes, one of them is Unity Shader Graph. Shader Graph is a visual tool to create shader in Unity. It's installed as a preview package by default from Unity 2018.1, but I recommend you to use Unity 2019.1 or above for a stable release, because at that version, Unity Shader Graph is marked by Unity as ready for production. When it comes to Shader Graph, you need to use URP or SDRP template. You might probably have heard about Unreal Material Editor or Shader Forge or Amplify Shader Editor. There are different visual scripting tools for shaders. Good news is they're based on the same foundation. After all, it means that everything you learn here from Unity Shader Graph could be applied somehow in those softwares. When you take a look at the shader graph, there are several nodes connecting. Let's begin to see what they are. The first thing I want to talk about in shader graph is the node. Node is the most basic unit of shader graph. A node could be used as an input, an output, or an operation. An input node provides data like colors, numbers, or textures. An operation node will take inputs to produce results like multiplying numbers or sampling textures. Then the result could be passed around to process in the next steps, and the data flow will end in some output nodes like preview or master. Each node has a unique function, and you can find a list of every node by the link I provide in the description. Understanding nodes is of course very important, but it's just the second most important thing to learn in shader graph. The first place belongs to the logic behind nodes combination. Each node is a processing step, then the leader image below each node is a result of that step. This is updated instantly whenever you change the inputs, and this is so helpful to help you preview and try different methods easily. There is a special type of node, the master node. Each shader graph has only one master node to contain the final shader result. You have to pick the master node wisely among lit, unlit, PBR, and VFX or blah blah blah, since it's not easy to convert a master node to another. And you might want to watch my previous video explaining the difference between lit and unlit shader by the link I provide on the screen. In the future, the master node will be changed to master site. Let's move to the ports. A port is a parameter of a single node. Each port is bound to a data type like color or number. In the node, ports on the left side are input, which gives data to the node. On the right side, there are output ports where you can take calculated result to the next step. On the screen, a multiply node has two input ports called A and B, and one output port which is calculated by multiplying A with B by normal math formula. I have to repeat it one more time. The image at the bottom of each node is a preview of the result, and this is one of the most useful features in shader graph because it gives instant feedback whenever there's a change. How about connection between two ports? That's an edge. You can connect two ports via dragging and dropping, and when there is an edge between them, the output port value is carried over via the edge to the other input port. And of course, in order to pass the value properly, the data type bound with two ports must be compatible, and we will talk about it later. You might be wondering, why shader graph? Shader graph helps us a lot to overcome pain points mentioned at the beginning. Firstly, it's a visual tool with instant feedback and preview, which is very convenient, especially for artists. Secondly, you just need to drag and drop nodes. No extra code is needed for basic usage. Of course, if you want, you can. Thirdly, you don't need to care about the syntax or the code structure, and the workflow is so obvious. You play with the nodes and the result is updated straight away. When there's an error, you know it exactly where. One more plus point: artists and engineers could cooperate much easier thanks to the subgraph. Yet it's not an almighty tool. It's only compatible for new render pipelines such as URP and HDRP, which requires new versions of Unity as well. Projects using built-in render pipeline are not supported by shader graph, unfortunately. Shader graph is still on the way to be improved, and it could never be as powerful as the true shaders. But don't get me wrong, shader graph is already very powerful at the moment I made this video. By combining a couple of nodes in different ways, you can still produce many convincing results. The only limit is your imagination. You might also ask, really? Why and how drawing links between blocks solve my shader problems? And the answer is, shader graph is not a shader. Shader graph generates the actual shader code with a visual scripting interface, and this is also the reason why it is always less powerful than actual shader codes. If you want to dig deeper into this topic, check the awesome presentation from Unite LA 2018. We can just plug it into the flow, and there's nothing changed with the rendering pipeline I described with the previous video. That's it. The nerdy time ends here. And with new knowledge about shader graph until now, I would like to combine what we gained from the first two parts together for a completed diagram. In the shader graph, we need to care about the lit and unlit shaders, and their node, port, and edge. The shader code will be generated by the shader graph, and it will be packed in a material. The material will be used by the rendering pipeline to render the final output. Now, let's get your hand dirty. In this video, we'll create a shader which mixes the colors back and forth over time, and that shader will be applied to make this glow. You need to install Unity 2019.1 or above with the Universal Render Pipeline. Before we begin, you should grab this beautiful model, which is created by Rai42 from the inspiration of the famous movie Tron Legacy. Some textures need to be pre-processed before importing to Unity. You could do it yourself or download the processed textures from my Patreon page. So let's take a look at the core idea of this shader first. Imagine that we have two colors and we could mix or blend them together with a ratio. When a color is put more than the other to the mix, it would contribute more to the final color. The mixing factor closer to the left means that the first color contributes more, and when it is closer to the right, it means that the second color contributes more. In shader, we use a range of 0 to 1, which is equivalent to 0% to 100%, to express the mixing factors of the colors. In order to change the color over time, we just need to update the mixing factor T from 0 to 1 and then reverse the direction. Keep repeating this process. We could create the glowing effect we want. This is a challenge for you. Could you create a final shader just based on this diagram? These are the steps needed to achieve the result we want. Firstly, we will create a new shader graph and then we will create a material associated with the new shader graph. And these two first steps should be done by yourself. The next step is assigning material to the disk. After that, we will create two color properties to mix them together. And finally, we will adjust mixing factor through time. Here comes the first step, create a new shader graph. In the project panel of Unity, click Create button and then select Shader P-Bar Graph. Give it a name like Glow. You can double click the shader graph to open it and you will see there is a node inside, which is P-Bar Master Node. You should create a new folder to store this shader graph assets. There are two types of folder structure for easier management. The first structure is you create a new folder for each asset type, like a separated folder for shaders, and then another one for material, another one for all the textures. And the second structure is you create a single folder for all the related sub-assets, no matter what types they are. Like you put everything of a character inside a single folder, including the mesh, the models, the animation, the texture, everything. You could find the folder structure that suits your need, but it's better to stick with one. Now let's move to the second step, create a new material. Firstly, select the shader graph asset and then right-click, create material. Moreover, you could see that the shader of this material is assigned automatically. Then give it a name like glow underscore Trondisk light underscore matte. Matte stands for material. Think about how you will search or filter for it later. You might end up with what's called a professional naming convention, but with your own rules. In the next step, I will assign materials to the disk. The disk uses two materials, one for the body, which is a dark part, and another for the glowing blade part. For the body, we could use a standard list shader which provides PBR textures. For the blade, we will use our custom material. Set up your own scene with camera, lines, and material for the disk. Now that you are all set up and ready to go, from now on, any changes of the shader graph could be observed directly in the scene. Let's create two color properties. I've mentioned about the relationship between the port and the data type previously in the NetD section. Now it's time to introduce some data types to you. Shader graph has several data types and we'll take a look at some of them. The first one is a number. Vector 1 is just a single number. Vector 2 is a pair of two numbers. Vector 3 and Vector 4 are just sets of 3 and 4 numbers. A slider is just a single number which is limited in range. If you are a programmer, you'll find the type integer and float familiar. There's nothing fancy about the numbers. Numbers are just numbers. So let's move on to the other data types, like the color. The color types is used to define a color in RGBA format, and a gradient type is used to define a gradient between colors. You cannot adjust it outside of the shader graph, at least for now. The last one I want to talk about is the texture. The texture is used to define the texture to be sample. Among them, color is truly a special one. It's actually a vector 4. Surprise? The color data is packed in 4 channels: red, green, blue, and alpha. Each channel could be represented by a number in the range from 0 to 255, or FF in hexa format. In shaders, these numbers are mapped to the range of 0 to 1. Then, a color is just a set of 4 numbers between 0 and 1. That's why a color type is compatible with a vector 4 type. Zoom in and you'll see ports with each data type having different colors. Do you notice that vector 4 and color type share the same colors? Ports with the same color are compatible. Moreover, all the number types are compatible through the promoting and truncating mechanics. You could find more details about the data types on the shader graph manual page, and I provide the link to this page in the description. Now we know much more about the data type and especially the color. Let's create two color properties in the shader graph. Select a blind spot and right-click, create node color. Repeat the step to create the second color. And then you can adjust colors as you want. If you try connecting one of those colors to the Albedo port in the master node and click Save Asset button, you would notice that the color of the blade in the scene changes accordingly, and that's how shader graph works. Nodes adjust medium to provide values for the master port, and the changes happen almost instantly. Awesome! Let's move to the next step. As long as the color is just a 4-dimensional vector, the mixing operation is just a mask function. Values in each pair of channels, including red, green, blue, and alpha, are calculated follow the formula of linear interpolation, as shown on the screen, with A and B are the numbers of each pair, and T is the mixing factor of B. Don't worry, you don't have to do the math. Shader graph has a node to calculate this formula called LOVE. Let's use this to mix the colors. Firstly, create a LOVE node to mix the values, and then set the colors as the values you want to mix. This means that you should connect two colors to the A and B part of the LOVE node. Then we need a number to control the mixing factor. The choices we have are vector 1 and slider. In this situation, we want to climb the range of the mixing factor from 0 to 1. That's why I choose a slider. Finally, set the LOVE output as Albedo in the master node and click Save button. You can play with the slider to adjust the mixing ratio. And in the next step, we just need to let time control this number. Time is just the number of seconds passed from the first day of 1970. So the range of time values is huge, if not infinite. On the other side, our mixing factor value range is very limited. So, with the intention of converting time into the mixing factor, we must find a function which transforms any number to another number in a fixed range. There are many functions like that, but I will pick the sine function. Why? It transforms x to a number in the range of -1 to 1, which creates infinite loops. Look at the graph. The sine wave is so smooth, which is ideal for applying easing to the motion. Let's use it. Firstly, create a time node, then set the sine time part as the mixing factor in the LOVE node. That's it. Lean back and enjoy watching your colors are mixed automatically over time. Wait, something wrong. The first color seems to appear longer than the second one. In order to debug these issues, I'll try to simulate the sine values by connecting a slider with the range of -1 to 1, and we'll see how LOVE node changes when we change the slider value. And there it is, I find the first clue. All the negative values lead to the first colors as a mixing result. It means that there's something behind the LOVE node. By referencing the shader graph menu page, I find out that the mixing factor is clamped to the range of 0 to 1. It means that all the numbers outside of this range will be forced to take the nearest numbers. In this case, sine function produces results in the range from -1 to 1, not from 0 to 1 as we want the mixing factor to be. All negative values are clamped to 0, and this explains why the first color appears longer than the second one. In order to fix this, we just need to scale the range from -1 to 1 into 0 to 1, so that any value in the range of -1 to 1 could be mapped to new values according to the ratio in the range of 0 to 1. This could be achieved by remapping. In Shadowgraph, create a remap node and set sign time as the input to be remapped. Other parameters of the remap node are already set up to scale -11 to 01, so leave as they are. Finally, set remap output as the missing factor, and that's it. Congratulations, you've reached the 100% completion level of this task. The two colors are fixed inside the shader graph. Let's make them customizable by using the blackboard. In the shader graph, select two color nodes and then right-click, Convert to Properties. You can click the blackboard button on the top right corner of the shader graph window and you'll see that the blackboard panel is open. In the blackboard panel, you'll see two color properties. You can rename them as you want and then click the Save As Set button. Now you could customize the colors via the inspector. Select the material and you see there are two colors could be changed to any values. See, just a small step further and you reach the 110% completion level of this task. How about the speed? Do you feel that the fading speed is too slow? Do you want to speed it up or even slow it down more? When it involves speed, we should think about how to enter the time factor. There's no better way to visualize it than the graph. In our case, the mixing factor goes up and down following the sine wave. That's why I have prepared some variations of the sine waves. You can look at them here or you can play directly with them in the Desmos webpage to see how it changes with some adjustment by the link I provide in the description part. In the graph, the sine function is drawn with the dotted curve and the distance between two highest points is the time needed to repeat the loop. That's the wavelength relating to the frequency of the sine wave. Now, let's see what will happen if we add an amount to the x or the y. The graph will be translated along the x-axis and the y-axis, but the most important point is the distance between two highest points doesn't change. It means that the frequency remains the same. On the other side, if we multiply an amount to the x or the y, the graph will be scaled horizontally and vertically. Look at the light blue graph, where I multiply x to a number a. The distance between two highest points changes whenever I change the number a. And that's the function we need to decide how fast the value can go up and down along the sine wave. Now, let's substitute x with time. You realize that if you multiply time to a number greater than 1, you are fast forwarding the time. On the other side, if you multiply time to a number less than 1, you'll be put in a slow motion mode, or even further, you can reverse the time. And this explains why we can change the frequency of the sine wave just by multiplying time to the number before fitting its result to the sine function. And we will do exactly the same in the shader graph. Go back to the shader graph and create a new number to act as a speed factor. You can multiply time with that number by the multiply node, then fit the result of that multiplication to the sine function, and finally connect the sine output to the remap node. Now you could control the colors and the speed like a god. This is a tricky question for you. We do not use the sine time part in the time node anymore. Instead, we create another sine node. Why? Leave your answer in the comment section below. Hey, that's a big step. You've reached the 120% completion level of this task. Okay, cool. So can I apply this shader to any object that I want to make it glow? No, not yet. Do you remember that this uses two materials? The black part is an individual material, so we are free to control the glow settings. With another object, we are not that lucky. For example, if we duplicate the material and apply it to this sci-fi crate from Sandgate Blaze, the entire object changes its color over time. This is not the expected behavior, because we just want some part of it to be glowing. In fact, I left a hint about the solution for this issue in the previous video. It's the emission property. When it comes to glowing light effect, the solution is using another texture called emission map to control the glowing areas. The rest of the objects still use albedo textures as usual. For PBR instead of WAP, you don't have to processing many different textures. This is a tedious and boring task. For example, you need to list all the textures needed and then sample them and then unpack the smoothing map from the alpha channel of the metallic map, not mentioning about tiling and offset, blah blah blah. You could do it yourself, or this task could be done quickly by using my PBR Avalanche subgraph. It's just a custom node where I deal with textures by a small shader graph packet inside. You can download this handy node from my Patreon page. It's very easy to use this subgraph. The input is PBR textures and parameters, and the output are the value that the master node requires. That's it. Let's use this subgraph to load an emission map to specify glowing areas. In the Trondic example, we chose to mix the albedo color. From now on, we'll switch to the emission color. Fortunately, there's no change to the core path. It means that the LURP and remap steps remain the same. You just need to redirect the LURP's output to PBR Avalanche emission color port. With that simple action, only specified areas are glowing. The rest of the script stay with the default albedo color. Let's go back to the shader graph to set up other PBR parameters for this script. Just by selecting the corresponding textures and adjusting the numbers, the script will be much more realistic. The textures of this script must be pre-processed just like this in the previous example, and you could download them from the Patreon page. Now, take a look at the script. The glowing parts are under control by our custom shader. The rest is rendered normally with PBR settings. This shader could only be used for the script because all the PBR parameters are fixed inside the shader graph. Let's make them customizable with Blackboard. You can follow the image on screen to check the data type of the Blackboard properties, and you might want to use the duplicate command with shortcut key Ctrl D and Command D to create properties more quickly. When the PBR parameters could be customized from the inspector, we could create another material using the same shader for this beautiful bike model. Amazing, good job fellas, it's a 150% effort. Speaking of glow, the emitted light should affect the surrounding environment, so it's time to apply the bloom effect. This is achieved by using the volume framework, which is installed by default in Unity. Follow this step to add the bloom effect to the scene. Firstly, create a new game object and then add the volume component. Secondly, set the volume mode to global so that these settings could be applied to any object. Thirdly, create a new profile of post-processing for these scenes, and then click Add Override and select the bloom effect. Finally, check and adjust the threshold and intensity parameters of the bloom override. Only pixels brighter than the threshold could be affected by the bloom effect. And the intensity parameter will control how much bright the glow is. One of the advantages of the emission is that we could control the emitted light intensity, and we'll do that by switching the color mode of color properties from default to HDR, which stands for High Dynamic Range. And this is the final result when we have bloom effect with HDR colors applied for many different objects. Even the animated Tron character from One Angelica 8 could use our shader without any problems. What a long video, isn't it? You deserve to reach the 160% completion level at this point. I promise no new features will be added to this graph. But guess what? Even in that case, there's a minor step ahead, and this is the arrangement. This step is optional for sure, but this is a factor that makes you professional. Just by arranging notes, putting them in the groups, and leaving a sticky note to tell others or remind yourself, you deserve to reach the 200 completion level of the task. Believe me, this very little effort is worth a try. From version 9, Shadow Graph introduced a redirect node which could be used to rearrange the edges, just like the node. Arrangement is so important that it gets official support from Unity. It's Google time. I have introduced a mathematical node which is the multiply node, and you can self-study about other mathematical nodes as well, like add, subtract, divide and modulo. Try to tell the difference between divide and modulo nodes because they will be used for tiling effects. There are other mapping nodes which are glance, saturate, minimum and maximum, and you can find out more details about them on the Shadow Graph menu page, or you can do experiments yourself because they're useful. And you might want to check other shaping functions like triangle wave, sawtooth wave, and try to replace the sine wave by those ones. And finally is easing, one of the most important principles in animation. Try to read the book The Illusion of Life from Disney to check out all the 12 principles of animation. To sum up, Shadow Graph is a great visual tool to generate shader code. And when it comes to mixing or blending, think about the loop node. And when the values are not in the valid range, think about the remap node to scale the shaping function. Thirdly, consider to adjust your shader to adapt with many situations. And finally, pack the Shadow Graph like a preset gift because it will be helpful for yourself or many other people. Do not procrastinate, start now. Try to remake the effects in the port and ask yourself hard questions like, what if I want to set various color for different spots? What if I want to randomize the glowing colors? What if I want to use a curve to control the mixing factors? Break the rules after understanding them. Finally, study more based on the Google Time section, just a tiny step further. Ayo, if you find something useful here, please like and share this video. And in order not to miss any video in this series, please subscribe this channel. If you have some comments or feedback, please leave them here, or accept our fan page on Facebook. And please subscribe our page on Patreon to read exclusive posts with full resources, including all the assets used in this video. Bye.